This is a general review of the concepts that we've covered when we've looked at waves. First, let's draw a model of what we're talking about here. We need some water. We need a boat. Here's our fisherman. That's his eye. Okay, then we need a fish. Let's think about why the fisherman can see the fish in the first place. So light is leaving the fish and headed toward the fisherman. The light that leaves the fish heads toward the fisherman's eye. When it changes media from the water here to the air up here, right here at this spot, it's going to speed up because light travels faster in gas. So when it speeds up, it's going to refract away from the normal. Well, where's our normal? Our normal is perpendicular to where the two types of media meet. Okay, so here's where the media meet, and then this is our normal. If it didn't refract, it would just head straight through to the fisherman's eye like that. But it does refract, again, away from the normal. So it bends this direction. What that means is, if we think about light getting to the fisherman's eyes, what the fisherman sees from one spot the fisherman may think is actually coming from a different spot. Let's think about that. The fisherman is used to light coming in a straight line. So light that comes this way from the fish, and then let's redraw our normal. Yeah, where's my eraser? There it is. Okay, the new normal is here because we always have to draw our normal where the light beam hits the interface between the two media. So now it's going to refract instead of going straight and continuing its original path. It's going to refract, and now the fisherman sees the front of the fish. But the fisherman may feel like, if he's not accounting for that refraction, he may feel like this is where that light came from. So he thinks the fish is here, but it's not, it's further back. So the fisherman may aim ahead of the fish with the spear. Okay, the fish isn't there, it's here, but it looks like it's further ahead. In the summertime, the sun is shining. Let's say we have two shirts. Over here, we have a dark shirt. And over here, we have a white shirt. Now we will draw light coming from the sun, and it is going to come down and hit each of our shirts. Whoop. Moved a little bit. Let's try again. Okay. So when it hits the white shirt, it's white light, which is made of red and green and blue light. That light is going to mostly reflect off of the white shirt. Keep in mind that here we have our normal, perpendicular to our surface, our reflecting surface. Most of the light will reflect. Now, when it comes to this shirt over here, because it's a black shirt, right, most of the light is absorbed. Very little light is reflected. any tiny little bit of light that's reflected will follow the rules of reflection and reflect out at an angle of reflection that is equal to the angle of incidence there. But most of that light goes into the shirt. It's absorbed, okay? And that raises the temperature of the shirt and the person wearing the shirt. All right, we're looking in a mirror. Here we are. There's our feet. Here's our mirror. I'm going to draw the mirror two-dimensionally. So there's our mirror surface. Let's give us a little more mirror. Okay, here's our mirror. Now, the reason you can see anything is because light bounces from it and enters your eye. So her feet, in order to see them, the light leaves the feet and then reflects off the mirror. Of course, let's see, here's our normal perpendicular to the surface. It's going to reflect this way. Well, if she's very, very tall, she might see her feet, because your eye would have to be here to see your feet. When you heard someone talking with the telephone cup activity, what you heard was from the energy moving down the string. So sound is a compression wave. That's why I've drawn this part right here. Okay? And if you were to look at this string, this is the string right here, if you took a tiny piece of it, you would see that when the wave traveled from one person's mouth right here, blah, 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 to this person's ear, as the sound wave traveled, parts of the string where the energy was in the compression part of the wave, the molecules would get a little closer. Then for the rarefaction, they'd get a little further. Now the string, of course, is a solid. It doesn't rip apart. So this movement and this distance is really, 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 really tiny. But it's enough so that when it gets here, because it's traveled down here, it actually transfers that energy to the air, and then you hear the sound wave in your ear when your eardrum vibrates. In this example, you can see this light ray or sound wave travel through medium 1, and then